In this video, we're going to look at ideal gases, specifically looking at the equation of state. This is the part 2 video of ideal gases. Now, the learning outcomes for this part: understand that a gas obeying PV is proportional to T, where T is the thermodynamic temperature, is known as an ideal gas. Recall and use the equation of state for an ideal gas expressed by PV is equal to nRT, where N is the amount of substance, and also use PV is equal to big N KT, where N is the number of molecules. Finally, you must recall that Boltzmann constant K is given by R over Avogadro constant. Now remember to subscribe to the Physics Tips for Cambridge Students YouTube channel. Hit the bell notification so that you get alerted of future videos. Without much further ado, let's get started. The equation of state. In my part 1 video, I was looking at the mole. The following quantities can be measured for a gas trapped in a flask: the volume of the gas, temperature of the gas, pressure of the gas, mass of the gas, amount of gas measured in moles, and the density of the gas. These are called macroscopic because they can be measured. Now we're going to delve into looking at gas laws, Boyle's law, Charles' law, pressure law, and the combined law. Boyle's law states that the pressure of a fixed mass of gas is inversely proportional to the volume, provided the temperature and other conditions remain constant. So if I'm to plot a graph of volume versus pressure, I'm going to get a graph that is like that. So these are called isotherms. This is at a lower temperature and this is at a higher temperature, the relationship between V and P. If I plot a graph of V versus 1 over P, it's going to be a linear graph. The one that is the least steep gradient is when the temperature is low, and then when temperature is high, you're going to get a steeper gradient. If I plot a graph of PV versus P or PV versus V, I get straight line graphs. Okay, this is for a lower temperature and that's for a higher temperature. Since V is proportional to 1 over P, therefore PV should be equal to a constant, where we then come to P1V1 equals P2V2. Then we move on to Charles' law and the pressure law. Now Charles' law states that the volume of a fixed mass of a gas is directly proportional to the temperature when pressure is kept constant, and the pressure law states that the pressure of a fixed mass of a gas is directly proportional to the temperature provided the volume is kept constant. So the graphs of either V or P versus temperature in degrees Celsius will look like this. So this is for different masses. This is a smaller mass and the larger mass. Then this is the absolute zero temperature minus 273.15. So what we can deduce from this graph is the volume and the pressure are not directly proportional to the temperature in degrees Celsius, but directly proportional to temperature in kelvins, because your origin will be right there if you're plotting against temperature in kelvins. So on Charles' law, we're saying V is directly proportional to T, so V over T will be a constant. V1 over T1 equals V2 over T2. Similarly, on the pressure law, we're saying P is directly proportional to T. This is thermodynamic temperature. So P over T will be a constant. P1 over T1 is equal to P2 over T2. Minus 273, like I said, it is the absolute zero, and absolute zero, that's the temperature in kelvins. Then we're going to summarize this when you combine the three laws. Since we said that for the first one, P is inversely proportional to volume, and then we said PV is equal to a constant, we had P1V1 is equal to P2V2. And then for Charles' law, we said V over T1 should equal V2 over T2. So as you can see, I've combined this law. So P1V1 over T1 will be equal to P2V2 over T2. The pressure law can be deduced from there, where you have P1 and T1 also coming there. P1V1 over T1 is equal to a constant, so that constant will be equal to nR. N is the number of moles and R is equal to the molar gas constant R, which is given a value 8.31 joules per Kelvin per mole. The ideal gas equation can also be written in that format: PV is equal to big N KT. PV is equal to nRT. So number of moles is equal to N over Na. So in place of that, I can put PV is equal to N over Na, then RT. Now if I divide these two, that's going to give me a new constant, which is small k, that's Boltzmann constant. This then becomes PV is equal to capital N number of molecules times Boltzmann constant times T. So that is where this is coming from. Remember, temperature T is in kelvins. If you say 8.31 divided by 6.02 times 10 to the power of 23, you are going to get 1.38 times 10 to the power of minus 23 joules per Kelvin. Right, so I'm going to define an ideal gas as the one that obeys the gas laws, Bohr's law, Charles' law, and pressure law. So when you combine all of them, it is going to obey PV over T is equal to a constant, or PV is equal to nRT, that is at all pressures, volumes, and temperatures. So equal volumes of ideal gases at the same temperature and pressure containing equal number of moles. 1 mole of an ideal gas at 273 kelvins, that's 0 degrees Celsius, and pressure 101, that's 1 atmosphere, has a volume of that. So this is called the standard condition, 22.4 dm cubed. So 1 mole of an ideal gas is equal to PV over T. P is the atmospheric pressure, V is the volume at standard temperature conditions and pressure, and then T is 0 degrees Celsius. So that's going to give that. So this is called the molar gas constant, R. Now I'm going to work out some problems with you. The first one, find the volume occupied by 1 mole of an ideal gas at STP, standard temperature and pressure condition. Remember, standard temperature and pressure will be 0 degrees Celsius, 1.03 times 10 to the power 5 pascals. We need to work with temperature in kelvins, so this is supposed to be used as 273 kelvins. So PV is equal to nRT. We want to find the volume, that is what's being wanted there. So volume will be equal to nRT over P. The number of moles is 1 from the question, and then R is 8.31, T is 273, 1 atmosphere, so that gives 22.4 dm cubed. The second example, a gas cylinder of volume 4 liters, remember 4 liters is 4 dm cubed, or 4 times 10 to the power of minus 3 cubic meters. It contains oxygen at 15 degrees Celsius and the pressure of that. Find the volume at STP, then the mass of the gas as well. So remember to convert this 15 degrees Celsius to kelvins, so that would be 15 plus 273, that gives you 288 kelvins. Now making the volume the subject, P1 V1 over T1 times T2 divided by P2. So if you do the maths, you're going to get 94.8 times 10 to the power of minus 3 cubic meters. Then to get the mass, you're given the density as 1.4 kgs per cubic meter at STP. Using the formula density is equal to mass over volume, the mass will be volume times density, which will be that 1.3 kgs. I'm going to end the video here. Please like, share, and comment as well. Remember to subscribe to the Physics Tips for Cambridge Students YouTube channel. Signing out.